Hey everyone, welcome to CafeQED. My name is Peter, and today let's talk about the chain rule for finding derivatives. So let's say we have a function which can be represented by f of g of x, or in other words, it's a composite function, which is a function that is a function of a function. But basically that just means that we're plugging functions into each other, like exactly what I've written here. And now the chain rule tells us exactly how to differentiate a composite function. So the derivative of f of g of x is going to be equal to f prime of g of x times g prime of x. And let me just quickly break down what each of the pieces mean for us in the chain rule. So first of all, before we can even apply the chain rule, we need to recognize what our f and g functions are. In other words, we need to know what the outer function is, which is f in this case, and then the inner function, which is g. Then, to apply the chain rule, we differentiate just the outer function f, giving us f prime. Then we plug g of x, our inner function, directly back into the derivative of f to give us f prime of g of x. Then we multiply by the derivative of g. So basically, the chain rule allows us to break down the differentiation process of a composite function into just differentiating the outer function, then differentiating the inner function, and then putting everything back together according to the chain rule. And while having a formula for the chain rule is great, I also want to bring up a slightly different way of looking at the chain rule. And this colloquial way will hopefully help us better memorize the structure of the chain rule. It is a product of two terms, where the first term is the derivative of the outer layer and keep the inside the same. And then the second term is the derivative of the inside. And hopefully with the color coding that I've been using, it's easy to match this formulation of the chain rule with the original formula representation of the chain rule. All right, let's take a look at some practice problems. For our first problem, let's find the derivative of our function, which will be the quantity 4x cubed minus 2x squared plus 7x plus 2, all to the fifth power. So the first thing that I would like everyone to recognize about this function is that it is a composite function, right? It's created by plugging in the 4x cubed minus 2x squared plus 7x plus 2 into the fifth power, or in other words, into a function of the form x to the fifth. Well, in order to take the derivative of this function, we're going to be using the chain rule. And since this is our very first problem for using the chain rule, I'm going to follow the formula expression of the chain rule to the t. So basically, I'm going to first specify my f function, then my g function. Remember, f is my outer function, g is my inner function. Take the derivatives of f and g, and then plug everything back in to the chain rule to get my answer. And then for the following problems, I'm going to start streamlining the process for applying the chain rule to show you guys what it might feel like to use it when we become more and more familiar with it. All right, so now coming back to this problem, I am going to let my f of x be the outer function, in which case this will be x to the fifth. And then I'm also going to let my g of x be the inner function, which is going to be 4x cubed minus 2x squared plus 7x plus 2. And if you're a little unsure of where I'm getting my f and g functions from, well, basically I chose them so that if I were to plug g back into f, or in other words, find f of g of x, this will give us back our original function of h of x. Okay, so once we agree that f and g are appropriately chosen, let's now continue on and take the derivative of f and the derivative of g separately from each other. And the reason why is because we're going to need these two derivatives in order to apply the chain rule. So we get that the derivative of f is going to be 5x to the fourth. And then the derivative of g is going to be 12x squared minus 4x plus 7. And now let's throw all of this back into the chain rule. So we get that h prime of x is going to be equal to f prime of g of x times g prime of x. And this is directly from the formula for the chain rule, which boils down to the first term is going to be f prime of g of x. So we're going to be plugging in g into f prime. So this will be 5 times the quantity 4x cubed minus 2x squared plus 7x plus 2, all raised to the fourth power, and then times g prime of x. So we're going to multiply this by 12x squared minus 4x plus 7. And this is what we get for the derivative by using the chain rule. And I mentioned this at the very beginning of the problem, but I'm going to mention it again. The work that I've showed here for this problem is a very rudimentary way of applying the chain rule. Basically, we specified explicitly what our f function is, what our g function is, we found their derivatives, and then we kind of plugged everything back into the chain rule formula to get our final answer. But for the next few problems, I'm going to streamline this process and apply the chain rule directly onto the function. So basically computing the derivative as we go. But don't worry, I will try to walk us through as clearly as possible so I don't lose anyone. Okay, so let's take a look at those. For our second problem, let's find the derivative of the function tangent of the quantity 4x squared plus x to the negative 1. And again, like the previous problem, this function is also a composite function. The inside layer is 4x squared plus x to the negative 1, and we're plugging that into the outer layer, which is tangent. Okay, so like I mentioned previously, for this problem, I'm going to streamline my usage of the chain rule by using the colloquial version that I brought up earlier. And I would say that this is how most people usually end up using the chain rule because it's much faster than having to set the f and g functions every single time. And we're going to see in our next problem that it's also very useful when we need to take derivatives of functions that are a little bit more complicated than what we've seen so far. Okay, so let's give it a shot. By following the chain rule, we get that f prime of x will be equal to the product of two terms. The first term is going to be, first, the derivative of the outer layer, and the outer layer here is our tangent function, the function highlighted in blue. And we know that the derivative of tangent is secant squared. So let's go ahead and write that down. We have secant squared. And then I'm keeping my parentheses empty, and the reason why is because the second half of my first term says to keep the inside the same. And our inside function is the function highlighted in orange, so 4x squared plus x to the negative 1. So according to keep the inside the same, I'm going to plug 4x squared plus x to the negative 1 back into secant squared. So again, what we've done here is we first differentiated the outer layer and only the outer layer, so we turned tangent into secant squared, and then we plug the inside function back in. And then our second term will be the derivative of the inside. And while this one is going to be a little bit more straightforward, right? Because the derivative of 4x squared plus x to the negative 1 is just going to be two applications of the power rule, right? So our first term will become 8x, and then our second term will be plus a negative 1 times x to the negative 2. And then simplifying everything out, we get, well, I like to move all of my non-trig functions in front of my trig functions. So I'm going to first write 8x minus x to the negative 2. And this is going to be times secant squared of 4x squared plus x to the negative 1. And this will be our derivative. And hopefully everyone can agree that this problem was a little bit more streamlined than our previous problem, right? We essentially were able to write down the answer in just one step. And this was just following the more colloquial, I guess if that's a good way to put it, version of the chain rule that I introduced. Okay, so now let's try this again on a slightly more complicated problem. All right, for this next problem, let's find the derivative of the function g of x is equal to sine cubed of cosecant x. Okay, so right away, I think we might all notice that this function is a little bit more complicated than before, even if we might not be able to immediately place our finger on it. And the first thing that I want to point out is the placement of that cubed, or the placement of the power of 3. While it's correctly placed to imply that we're raising sine to the third power, I want to rewrite this function so it might be a little bit more clear as to what the layers are in this composite function for when we take the derivative using the chain rule. So I'm going to instead rewrite this function as the quantity sine of cosecant x and then all cubed. And these two are exactly the same. It doesn't matter if I place the cubed on the sine or cubed on a larger set of parentheses around the sine. They both mean the same thing. Okay, and then from here, we might be able to spot that there are actually 3 layers going on in this composite function. The first layer is the cubed, the second layer is going to be the sine, and then our third layer is the cosecant x. And so now you might be wondering, well, we've only seen the chain rule for composite functions with 2 layers, like what's going to happen with 3 layers? And I promise you that we can do this. The chain rule that we saw earlier is exactly enough for us to figure out how to differentiate something like this. And the approach that I want to take here is to first not think about sine and cosecant as two separate layers. They are two separate layers, and that's going to come into play a little bit later. But for now, let's think of them as only one single layer. And now we see our function as just a composite function with two layers, right? The outer layer is the cubic term, and then the inner layer is this sine of cosecant x term, which again is actually two separate layers, but we're going to treat it as one single layer. Okay, let's apply the chain rule to take the derivative. So we get that g prime of x will be equal to, the first term will be to differentiate the outer layer. So that's differentiate the cubic term. So we're going to get 3 times something squared, right? And again, this is only differentiating the outer layer. And then we're going to keep the inside the same. So we're going to plug the sine of cosecant x, our orange colored function, back in. So this is going to be sine of cosecant x on the inside. Then my second term will be to differentiate the inner layer. And for now, I'm just going to write out that we need to take a derivative of the inner layer, which will be sine of cosecant x. Okay, so far, we've just followed the chain rule as we know it. We haven't done anything fancy just yet. And we are now here. We need to take a derivative of sine of cosecant x. And do we recognize what's going to happen here? This is another derivative of a composite function, right? This means that we're going to be applying the chain rule again, where this time the outer layer, or the outer function, is going to be the sine function, and the inner layer will be the cosecant function. Okay, so let's go ahead and apply another chain rule. So we get that this will be equal to, well, my first term will stay exactly the same, so this will be 3 times sine of cosecant x, all squared, then times, and now for the chain rule, we're going to first differentiate the outer layer, which is our sine function, our blue function here, which is going to be cosine. And then we're going to keep the inside the same, so we're going to plug cosecant x back inside. And then we're going to multiply this by the derivative of the inside, or the derivative of our orange layered function. And the derivative of cosecant is negative cosecant cotangent. And that's it. This is our derivative. But I'm actually going to clean this up just a little bit. I want to move that negative sign out to the front, so it's much more clear that we have a negative sign. So we have negative 3 times sine of cosecant x squared, and then times cosine of cosecant x, and then times cosecant x times cotangent x. And here is our final answer for the derivative. That was kind of neat, right? Even if we're given a slightly more complicated function in the sense that there are more layers, we still know how to handle it, even though the chain rule that we were originally given only specified taking a derivative of a composite function with only 2 layers. And the magic, or the trick, happens when we need to differentiate the inside again. And the derivative of the inside, as we saw here, could very well be another chain rule. So yeah, I hope that everyone was able to follow along with that example. But if not, don't worry. It just takes some practice to get used to the chain rule. Alright, so that's all I have for today. If you have any questions, leave a comment below. If you enjoyed this video or found this video helpful, give it a thumbs up. And if you'd like to learn more math with me at CafeQED, hit the subscribe button. And I'll see you all next time.